Thank you.
I mean,
enjoyed your presentation. Thanks for all the answers. Don't keep at it, you know?
I know, but I've been telling these people. Remember the old days when Kurt banded out 200 pounds and
Yeah, I was in a different world. What are you doing? I'm in Lightroom, been there for 5 years. You don't know what I'm telling you.
It's fun. I mean, actually, that's the part of these books. Nice, simple code that shows one idea, and I really enjoy it.
I had a funny experience recently. You know, I've been doing all the great stuff, and I just thought, I'm going to replace my fixed function for the stupid little graphs or whatever I draw. And it was like, seven lines of vertex code.
I know.
And it's so much better.
I've been trying.
You know, I'd heard people say that, but I just, you know, I didn't know.
I've been trying to convince someone, you know, Cleve Wallen, he's an old friend of mine, goes back to and he's moved back to Santa Fe. And I'm trying to show him, I'm doing 1,000 by 1,000 PVE on my cell phone, and it's running really fast. No, it's not bad. It's pretty amazing. Yeah, I mean, we realize that our students just don't believe it. You tell them what we used to do and what used to be a big problem.
I hate to learn like shaders because it's more like you have to learn C first.
No,
many students don't learn C anymore.
It's the JavaScript branches that are trying to keep elucidating. Some of them, they have real trouble. You know, the ones that are serious, they have JavaScript scope is so different than anything that they've learned. That's a problem. There's some real weird ones that pop up because there's only one more. It switches back and forth between strings and numbers because it thinks it's the right thing to do. I found a weird one that my code's been running all of the time, and then I found somebody said, oh, it fails over here on sliders. Well, it turned out it was conveniently changing what input from the slider turns out it's a string. I mean, I didn't realize that. But if you use equal, it doesn't care.
Right.
So there's just all kinds of oddities that get thrown there. Students are used to people in the movie. So I think all the programming is, here's a 10-hour course on Java. Here's a 10-hour course. And now you ask them to write something they just throw
in Australia, I gotta go over there.
They just really do much better.
So therefore,
My main goal is to like application
four profiles, so lost all the stuff.
It's kind of yeah. So I'm trying to make my constitution. Yeah, exactly.
Well, I was, but I couldn't. A lot of
exactly.
Anything else, if you had a strict non-compatibility.
Yeah. No, not at all.
Yeah, it's all better now.
We are sitting next to each other. You know? Yeah, it's 3 people, but
If you use it,
what do you use?
not full time. I'm not full time here. It's like we are like people from other teams, but the only person who's actually working full time is Joseph. I hope like I will transition on this, but I don't know. What do you do?
Oh, this needs to stay.
I'm sorry.
so that was when I started.
No problem. Our session hasn't started yet.
Yeah, but because that sliders, just 2 lines of code. Thank you so much. You could add finger gestures to that is I know. It was good to see you. I was looking for one.
There's an API that allows you to combine GPL, massive chip laboratory data on where the stars are, where the planets are, for geocentric
Oh yeah. I'm glad to hear that you're the one that creates like because you feel good. But it's a good risk for you to take.
You know, it's my editor was really good. He said we just forced the things that he would go to a shader and people, your faculty are concerned. They don't want to change it. So we really had to sort of oppose it. And he says now it's 2 years later, and nothing to change it. And that's when I pulled out myself and said, this is why.
So what's your students like? Are they freshmen or they are not
a lot of them was
Why is this not working? Can I hear myself? Hey, it's working.
It is.
Folks, let's try to get started. We have a terrifyingly packed agenda, and we don't get any beer until we're done. So we really need to get into our seats and ready to fire away.
So we just met.
Boy, it would be nice if this thing didn't blank. You have to choke up on these things or it doesn't work. I think we're going to have to hold it. This is going to suck. No, it's because it's filled. Yeah, that's totally awesome. Okay, I can tell it's been a long day. Maybe it's been a long SIGGRAPH already. I am hoping that all of my speakers are here. I see at least the one who comes after me. So that's good. We'll go from there. Welcome everyone. My name is Tom Olson. I am chairman of the ES Working Group and the Vulkan Working Group. This is the second annual PAN 3D Khronos BOF. So we're going to talk about all of the 3D APIs except WebGL, who just had their own thing, which was awesome. And if we had included them, it would have been 3 hours instead of 2. So I'm glad they did their own. The way it's going to work, Neil Trevett, our illustrious president, is going to give an overview of how Khronos works in the 3D space. We have an interesting sideline, which is the data format spec created by Andrew Gerard, which we just published. He's going to talk about that. He's going to set a world record by covering 19 slides in 3 minutes. Then Barthold will give the status update from the OpenGL Working Group, and I'll do the same for the ES Working Group, both of us ably assisted by some other members of the group. And then hopefully that takes an hour, and then we will shift gears and go into the to Vulkan mode and give a report on the status of the Vulkan project. So without further ado, please welcome Neil Trevett, Khronos President, and NVIDIA Vice President.
Thank you, Tom. I have to do this like super fast speed. So
we want to just kind of give the context and the overview before we started diving into a bunch of details. And hands up here who hasn't heard of the Khronos group before. All right, see, I saved the whole slide. I'm going to put that one in next time. All right, so in all of the outreach, in all of the press briefings that we've been given, this is the first slide we always put up, because I know Vulkan and Sphere are nice and shiny and new, but the really important message is that all the traditional APIs that you all know, like OpenGL, OpenGL ES, OpenCL, are not going away. In fact, you'll see, this is all the news items. I'm not going to go through them. You'll hear about them in a second. But we're developing all of these APIs. They're all developing in parallel, and they're going to continue to develop in parallel because they're addressing different needs. Each API is addressing different needs. But it is the new generation APIs that are shiny and new. So that's been a lot of the conversation here at this SIGGRAPH. And this was kind of the same slides we put up last time. The three new generation APIs, the core differentiator for Vulkan is that it's cross-platform. And that's not some abstract concept, for independent software vendors, independent hardware vendors, which is the vast majority of folks in this room, being able to have broader reach and lower cost. I mean, that's real, that's business. That kind of counts. And so we need to make sure that the open cross-platform standards are strong. But what does cross-platform mean? Well, we're making some announcements here during the show. A number of platforms are going to get Vulkan support. Microsoft is not adopting Vulkan per se, but just like OpenGL, the hardware vendors are going to be shipping Vulkan across many different variants of Windows, from XP up to Windows 10, and it's worth just noting in passing that DX12 is only for Windows 10, so even in the Windows ecosystem, cross-platform has value. But in some ways, even more fundamental are the platforms that are explicitly reaching out and using Vulkan as part of their platform definition. And from the get-go, Valve has been super supportive of Vulkan, and hats off to them. SteamOS, they've already announced back at GDC, is going to use Vulkan. Here at the show, we have the Linux community beginning to come on board. So we have Canonical for Ubuntu and Red Hat, both Khronos members, both supportive of Vulkan are coming out saying we're going to support Vulkan natively. And I think that's interesting, not just for the client side of Linux, but also for the cloud and the server part of the Linux market. You have Tizen, which is a mobile OS from Samsung, so we're getting quite broad coverage, but I think it's worth just taking a moment just to acknowledge that probably the biggest news for Vulkan coming out of this show is the fact that Android is going to be adopting Vulkan. And it's kind of historic. They could have done a metal, we could have had perfect fragmentation, but they actually decided to do the right thing, I think not just for the industry, but for Android. So really hats off to Google for really helping us all along. This has been an interesting show. It's been the first time we've actually had the chance to really speak to developers kind of using the very early Vulkan and DX12 drivers. What's their experience in Metal too? And I've taken the extreme liberty of paraphrasing Aris's talk for the next generation API session yesterday, the 4-hour session, down into one slide. And that was, Metal isn't quite so radical a leap because they've retained things like the object model, so it's easier to port, and it's actually a pretty good API. Vulkan and DX12, we kind of go all the way, we go all in for explicit control. It means that if you're starting with an ES app, you probably have more work to do to get to fully optimal, but it's worth it because the extra explicitness does give you benefit. And I went up to Aris after the talk and said, so, is it worth it? Extra effort for the return, is it worth it? And he said, yes, it is worth it. And I think it's more than just being able to further optimize your applications. The power and the low-level explicitness of Vulkan, we're getting ready for a 3-layer ecosystem. So what do I mean by that? There's 3 different ways that developers are going to be able to tap into the power of Vulkan. Of course, any developer is welcome to optimize for the explicit low-level API. A lot of the momentum behind Vulkan is from the games engine developers who are going to get excellent performance. And lots of people, of course, will use games engines. But then there's this other interesting layer in the middle, which we get to see how it evolves, where middleware and engines and tools and languages are going to be evolving to meet all kinds of market needs and create new market opportunities that we haven't even imagined yet. And I take encouragement from that because we've just seen in the last BOF the power of a 3-layer ecosystem. WebGL, when it first came out, was considered to be way too complicated for a web standard. But in hindsight, having that low-level, powerful API gives a diversity of middleware, enables a huge market opportunity. I think we're on the verge of seeing the same kind of dynamic happen in the ecosystem with Vulkan. Are we going fast enough? Right. Okay, so ecosystem is the thing, and I'm not going to go read this because we're going to get into more details, but in parallel with developing the spec, we're doing everything we can think of to develop an in-depth Vulkan ecosystem. Open source conformance tests, better documentation, tools layers, open source tools that plugs into the tools layers, much more flexible Windows systems integration, and Spear V. And not being talked about anywhere else, so I've got permission for Tom to spend 30 seconds on Spear V. Spear V is, I think, just as transformational as Vulkan. It's putting the first cross-platform, cross-vendor intermediate representation that natively understands compute and graphics. It's the perfect place to enable two communities to communicate and independently innovate. The hardware guys can just worry about how do I ingest and accelerate SpearV the best I possibly can. The software guys are now free to use SpearV as a backend for all manner of languages, tools, frameworks. And for developers, you don't have to ship binaries anymore. You don't have to do the front-end compiling. It's just win-win-win all the way around. And ecosystem, again, we're putting more details on how we're building out the SpearV ecosystem. We had the OpenGL BOF earlier this afternoon. Those red boxes there are the boxes that here at SIGGRAPH, Khronos are committing to put into open source. So we have the OpenGL, C and C++ translators, the GSL translator, assemblers, validators, which is very important for front ends, and round-tripping to and from LLVM. So I think a lot of people will use both LLVM and SpearV in their toolchain. We love LLVM. And even as SpearV is not even finalized yet, a quick Google gives dozens of open source projects already using SpearV. So there's now a .NET translator, so you can use C# for doing the shaders if you want. There's Haskell translators, there's virtual machines, debuggers, all emerging already out of the open source community. This is good ecosystem karma. And I think this is my last 2 slides. This is the same list of APIs, and I think I've put the possibilities in red here so we don't give all the working group chairs aneurysms as we talk about a roadmap, but there's super rich possibilities to begin to mix and match appropriately the different technologies that we have. For example, taking all the heterogeneous learning that we have in OpenGL 2 and shared virtual memory, single source programming, begin over time in the appropriate rate to start building that kind of functionality into Vulkan to build out the compute capability. We can potentially take Spear and have OpenGL ingest Spear. Why not? That might create a lot of interesting opportunities. And then the last thing, it isn't mentioned anywhere else, but I want to mention it because it's a call for participation. We are restarting the safety critical working group, not just using OpenGL ES, but potentially using Vulkan and Spear. So I don't know how people remember OpenGL SC 1.0, done 10 years ago. Very narrow market. The avionics guys needed a safety certifiable API stack for their Compass type displays. Well, that's actually been shipping, but it's obviously a niche market. The avionics guys are now being joined by the automotive guys, and obviously gets a much more significant shipment numbers, wanting to do electronic consoles. So there's a low-hanging fruit to bring shaders into OpenGL SC. That would be probably the first task for the safety critical working group. But looking forward, we're about to be surrounded by autonomous vehicles, robots, drones of various shapes and sizes. They're going to need lots of vision, compute, and graphics that are going to be safety certifiable. And the safety critical working group is going to be repurposing all of the technologies that we have in Khronos into that new emerging opportunity. Thank you.
Hello, everyone. Hello, everyone. Hi. Cool. Right. So this is a specification about communication. So who here hasn't heard of the data format specification? Okay. Yeah, I thought that might work less well than the Khronos one. So yeah, this. Don't stand on that cable. This specification is an extremely dull thing that's trivial that everybody has to do. I'm allowed to say that because I wrote it. I really hope this isn't the most exciting spec you hear about this afternoon, but it's still an important thing to have to do. So, good news is that some of you can ignore me and go to sleep for a bit, for 2 minutes. The question is, are you writing a program? If that program has to work with images and textures and that kind of thing, which I suspect will be some of you, and it's stored in memory, and you need that content to be described to anyone else. So if you've got pixels that need to be interpreted by anyone, and if you've got more than one of those things, you've probably rolled your own emails by now. And if you need to talk to hardware vendors or anything like that to make it work, then I'll need 2 minutes of your time, I'm sorry. So this is about formats. And formats are a fairly common thing for people to worry about. You've got some bits that correspond to some data in memory, and you're doing something with them and you want to know what they mean. And you say, oh, they're RGB, obviously. And when you said RGB, did you mean that kind of RGB, or did you mean that kind of RGB, or did you mean that kind of RGB? Or which order were they in? Because you pick the obvious order, which could be that order, or it could be that order. And around that point, I find a mouse pointer, and ooh, lag. And you decide that you need more than one of these things, and you need to read some data from elsewhere. At some point you get it wrong, and that happens. So then you decide that you've got all the bits in the right place, and hopefully it looks kind of right, so you pick some standard colours. So you need to work out what all those channels meant, what ones are red, green, blue. You know what red, green, blue are. Unless you realise that they're not quite the right red, green, blue, or they're very much not the right red, green, blue, because you've got the gamma wrong, or you've got the wrong colour space, or you're outputting to a TV, and which TV, because of course there are lots of them. And then around this point, you take a guess as to what it was supposed to be doing, and then the colleague who's trying to do everything like this right comes and does something like this. Yes, an expression of the value of my work. So then you decide you want to output video, and you think YUV is a good thing, and then you discover there's more than one YUV, and then you decide you want to use compressed formats as well, and then you decide to connect to a camera, and there are Bayer formats, and they've got some metadata, and it all gets even more complicated. And then you get it all working beautifully in your application, and you know that you're connecting it to something that works beautifully, and then you plug it all through a library in the middle, and that doesn't know anything about any of it, and it forgets all the useful information you worked out. So, generally speaking, I got to this point, and then I wrote a Khronos specification. At some point we should work out a Khronos specification for making video work even faster. Yes. This ought to be easy. Nothing quite does it right, because nobody really cares when they start out doing this. You do something specific to the problem space, and you knew what your problem space was, and then you need to work with something that's outside that problem space, and you end up hacking it a little bit. So you roll your own mechanism for doing this, and that's fine until everybody needs to talk to each other. And if you're an integrator like us, we have to spend our time trying to make them work together. And not everything is as far apart as you might think it is, especially if you're trying to read the spec to work out what's happened. So there's a data format specification. It's even newer than any other Khronos specification you've looked at. It's 2 weeks old. It's extremely dull. I speak from experience as a spec editor. Please read this so that you don't have to do it yourself. It's descriptive. It's a block of data in memory that says this is what this format means. It's done in one true way, so you don't have to read the English version, and you can write code that's extensible and can interpret that data so that you can handle formats that you never even heard of when you were reading the block in, and you can extend it to add extra proprietary information as well. It's versioned so we can screw it up the first time and then it'll work the second time around. It's flexible. Every format I can think of works in it as standard, and you can extend it to handle even weirder stuff that you couldn't possibly do normally. It's not very big, print it out on a few pages, go and read it on the toilet, use soft paper, and you can use it for more than one thing. There's no conformance, unlike most of Khronos stuff. It's not tied to any other Khronos spec. It was dealt with under the EGL group, but we're just doing it as a donation to the community because we got bitten by this in Khronos, and we'd like everybody to not get bitten by the same problem. And best of all, there was a press release about this, and absolutely nobody in the press is a software engineer and could work out what the hell it was about. So there's a link. Go and have a look at the link. I won't spoil the plot for you. Oh yes, and by the way, this is my fault for using practical effects at SIGGRAPH rather than anything else. But if you, to avoid you having to go through this kind of pain, then yes, please look at my spec, and then hopefully I'll never have to come and kill you. Thank you.
That was pretty awesome, Andrew. All right, Tom, how are you on time? Go quickly, Tom says. All right, my name is Barthold Lichtenbelt. I'm the chair of the OpenGL Working Group, and I work for NVIDIA. All right, we are announcing, we did a release a couple days ago, 13 new OpenGL ARP extensions, which I bucketized into 3 buckets. We have graphics pipeline operations, texture mapping functionality, as well as new shader functionality. If you add these numbers up, it's actually down to 14, and that's because I counted one spec twice. All right. So before we go into the new functionality, a brief update on where we are with OpenGL driver support. This slide Christoph makes, and thank you for that, Christoph. So green is NVIDIA, red is AMD, blue is Intel, orange is Mesa, and gray in there is the Mac. So you can kind of see where we are with extension and full support now. Over the last year, this is kind of what happened. So AMD increased the support from OpenGL 4 to 4.5. Mesa made a big jump, went from 3.3 to 4.1. It's really cool to see that. Intel added OpenGL 4.3 support, is making good headway in 4.4. And then NVIDIA has been supporting 4.5 since SIGGRAPH last year, and announced support for the 13 new ARP extensions this week. Okay, also news here. In 7th edition, well, yes, the 7th edition of the Super Bible is out. You can buy it on the shelf for today. Are you here somewhere, Graham? Thank you to Graham. He's over there. He updated it to version 4.5 and a bunch of ARP extensions. And if you can find them, there are some books available that we can give out as prizes for the party afterwards. But so far, the books are being missing. Hopefully, we find them soon. Okay, another update. The GLSL slang reference validator is the front end to the OpenGL and OpenGL ES shading language. It's a very strict implementation of the specification. You can run your shader through there, and if it compiles, it should also compile on the actual hardware implementation you're using, and vice versa. If it doesn't compile and it throws an error, your hardware implementation should also throw the same error. The asterisk is pending some hardware implementation details, specific details there. It's been continuously updated. It has almost all of ES 3.1 plus AEP support, and 3.2 support is coming, as well as most of GLSL version 4.x. Arrays of arrays are being added. As per V translation is there now, disassembly and encryption as well. And also we moved it over to GitHub, and that seems to be a positive thing. We're seeing some community involvement there now. Okay. Next thing, performance testing for OpenGL. We announced for Performance Suite last year, and over the last year we have made continuous progress. So we've added many more tests for both OpenGL 3 and 4 functionality. So the bar is being set higher and higher for OpenGL implementations continuously, and this is an ongoing thing. And then the last slide here on the ecosystem news in blue, been around for a long time, has updated already to the 13 new ARP extensions, so you can start wrangling today if you want to. Okay, let's move on. Let's talk about the graphics pipeline operations. 5 new extensions here, and we'll go over each of those in hopefully quick time.
Here we go. Fragment shader interlock, maybe the most important one out of the batch of 13 and the most interesting one. So it provides reliable means to read and write fragments pixel state from a fragment shader. The image here on the right of the slide came from Intel. That's where they're rendering this car using a frame buffer format, so floating point frame buffer format that the hardware doesn't natively support. So they did all the blending in the fragment shader using fragment shader interlock. So why is this new extension needed? Well, I'll play a quick recap first. Here I'm showing you 3 triangles, the red, the blue, and the magenta. And I marked 3 fragments in these triangles, and they all overlap, and they map to the same pixel in the frame buffer. So OpenGL requires that if this is the rasterization order from left to right in the yellow arrow, that the blending, the depth test, the stencil test, and the blending happens in the same order as well. Okay. Now, fragment shading, which comes right before depth, stencil, and blending, it's a massively parallel operation, so a fragment shader will likely take these 3 triangles, batch them all into one batch, and operate on and execute them all in parallel, not necessarily in order. So put those 2 together, you get fragment shading operating in parallel on all your fragments, and then the hardware takes care of the output of the fragment shader and makes sure that the order I just talked about is being preserved, and then depth, stencil, and blending happens in the right order. Now the interesting thing is, if you now start to actually access pixel data in your fragment shader that belongs to one of those 3 fragments that overlap, that's just unsafe in the sense that your results, if you really read or write to that pixel, will be undefined, as you don't really know what order the fragment shader is processing your 3 triangles there. That's why we need fragment shader interlock. So interlock guarantees pixel order of shading. And how it basically works is we take these 3 triangles, batch them up in 3 different batches, and each batch gets processed in order. Now that will have some amount of performance impact, but if you want to read or write in your frame buffer doing this, then this is probably a good trade-off for you. To give you a practical example of how this might work, so we take this stamp for bunny, here's a G buffer, here's the normal map rendered in the G buffer of the bunnies in the normal way. And now we want to apply this brick decal that show at the bottom here of the image in blue to your normals. And then the top of the image kind of shows in the shaded red where we're going to apply our brick pattern to the normals in the G buffer. Now here is where interlock comes into play. You use fragment shading interlock, you read in the G buffer your normals, you then blend in the brick pattern, renormalize your normals and write them out again to the G buffer, and then the result is you're shown on the 3rd image. Once you've done that, using fragment shader interlock, you can do your normal shading pass, and this will be the end result. So you haven't actually modified the geometry and just used the perturbed normals and the G buffer to do this. Maybe a more interesting example here on the left, you might have some geometry rendered with the normal map shown, and then maybe this is a game, you want to show some bullet holes that were shot into this piece of geometry, and you could do the same trick. You just use the normal decal map in the bottom right that has the bullet holes already encoded into it, but you need to use fragment shader interlock to do this correctly. So what does this look like in fragment shader? The thing to remember is you need to use begin invocation interlock, and then do your code in there where you read and write the frame buffer, and then you end up with invocation interlock, or simple as that. Okay, next feature. We have programmable sample positions right now. Added now as an extension on the left side, you'll see an MSAA 8x pattern that's defined by the hardware. And on the right side is where you can define, in this case, a horizontal pattern, how you would actually like to sample your pixels. And an interesting application of this will be you have 2x AA, and you can have a pattern this way, shown on the left, and then the other frame you're going to render again with 2x AA pattern on the right, and if you combine those 2 together, you get sort of a temporal 4x AA aliasing for the price of 2x, which is awesome. So this animating GIF shows you how that might work. Okay. Next, vertex shaded viewport and layer output, very simple extension. It used to be that you could only output viewport index and viewport layer out of the geometry shader. Now you can also output it from the vertex shader and the tessellation shader. Next one, early fragment test and post-depth coverage. So the default behavior of OpenGL is as follows, that the rasterizer produces a sample mask, it gets past the fragment shader, and then the stencil depth and color blending happens. In OpenGL 4.2, we added the ability to do early stencil and depth testing, but the sample mask still came from the rasterizer and passed to the fragment shader, which is probably not exactly what you want. So now with the post-depth coverage extension, we fixed that, but the sample mask comes actually after the stencil and depth test, so it will represent the right thing and pass to the fragment shader. Okay, next extension, ES 3.2 compatibility. As the artists always try to make OpenGL a true superset of ES, and there's always some functionality missing in OpenGL, so we added back with our ES 3.2 compatibility extension in this case. Nothing too exciting, but it's there. Okay. Texture mapping functionality. We have 3 new extensions in the texture mapping bucket, so I'll go over that real quick. Reduction mode. So normal texturing, when you do a texel fetch, you filter, and the filter will probably return you the average of the surrounding texels that you're used to. Now you can also ask for instead to get the minimum and maximum value of the surrounding texels to be returned to you, which can be really useful in, for example, volumetric rendering. In the top right here, this image you see normal volume rendering where the arrays are being blended, and then the projection of the 2D image is shown there. But sometimes you might actually want to find the maximum and minimum value in the volumetric rendering on the bottom right image here, which is especially useful in medical imaging. So again, on the left side is normal volumetric rendered image, but you might miss some details. So with maximum intensity projection, finding the maximum value around the array, you get all those details nicely come back to you. Okay, sparse textures. We added sparse textures in 2013, as you might remember. Right? Textures can be huge, maybe bigger than your video memory, so not all of it can be resident at once. So sparse textures solve that by making partial residency a possibility. However, our sparse textures did have a few issues, so we fixed that with sparse texture 2. In particular, if you were doing a texel fetch and the texel was falling into a piece of memory that was actually not resident, you wouldn't know. The result was undefined. And worse, there wasn't even a query you could even find out if that happened or not. So that was fixed with version 2, and this version 2 also supports sparse multi-sample and multi-sample texture arrays. On top of that, we also did a sparse texture clamp function, which adds an LOD parameter to the texel fetch functions, and it provides the floor of the LOD that the hardware computes for you. So if you already know that at higher min-map levels nothing is resident, you can set that floor and you don't waste trying to fetch stuff that isn't there. So how would that work? Here's a simple code example. You use the resident function and you loop over it until you get a hit, basically. So to give you a simple example, the green fetch here on the highest level will be an immediate hit because it's resident. The 2 fetches, the purple one, the first will be missed, the second will be a hit, and then the blue one, you have 2 misses, and now maybe the third time it's charming, you get protection. If everything was properly populated, you obviously didn't have to do that, but that's not the case. Okay, new shader functionality, set of 6 here, and here's where I counted our ES 3.2 compatibility twice, so I got to 14 total. We also have the ability now to actually exactly get the dialect, if you will, ES GLSL in OpenGL. So you just say pound version 320 ES, and off you go in your desktop implementation. Okay. This might be interesting. We added the ability to tell the OpenGL driver, please use more than one thread to compile and link your shaders in your programs. And also we added a non-blocking query so you can figure out if the link or compile is still ongoing or actually has finished. We also added 64-bit integer data types. That's super exciting. We have integer uints and vector versions of that. Added the GLSL note that we already had. 32-bit data types, obviously, and 64-bit floats, but this is new. 64-bit ints are new. Okay, shader ballot and broadcast adds 1 new function, which is listed on the bottom. Ballot ARB, which evaluates a boolean across all shader threads or invocations of a subgroup, if you will. And note that in a subgroup, not all shader threads or invocations might be active because either you have divergent branching or early shader exit maybe, and then the return value is put in a bit mask. So this allows for efficient collective decisions within a group of invocations. Shader atomic counter operations, we added those in 2011, but there was very limited things you could actually do and perform on these atomic counters, so we added several more options here. You can do adds, subtracts, minimum, maximum, bitwise operations, etc. And then this might be interesting too. Some ISVs were really asking for this. They wanted to get some idea of the performance of the shaders they were writing, so we added a simple idea as a clock counter that you can query. It's the only guarantee you get out of this counter that it is always increasing. We don't know what units of time they are. You don't even know if this shader will result, this clock will give you the exact same value the second time you call your draw call. But it can be useful to actually get some relative performance data out of the shader you're thinking. Okay, and this is my last slide. So this was a thank you multi-vendor efforts of many people, and put these spec errors and leads on here on the slide here. As you can see, through multi-vendor effort again. That's it. And then Christoph's going to come up here and he has a 5-minute or less demo he promised me on what Unity is doing with OpenGL.
So I don't have really a lot of time, but I just would like to show you our support of OpenGL that we are working on. And so for a while I've been very, very sad, and I had a butterfly in my tummy. When I was opening the editor, it will run with Direct3D, and that's not the good idea. So now, as you can see maybe on top, it's running with OpenGL 4.5. The thing that we are rendering, it's on this project, it's the one we used to demo our new Unified release at GDC, and we provided a package for the user just to learn from it, and yes. So what we are seeing, it's this thing which actually work with OpenGL 4.5, and it's a bit heavy for this computer, but so that's our blacksmith demo, basically. Well, that's basically it. I have a few slides. So I'm going to speak about the OpenGL support in Unity 5.3. So we are supporting a wide range of OpenGL version, which include ES and desktop, but also WebGL. It's a feature parity with Direct3D 11, and everything is a first-class citizen. So if you write your shader with Unity, it will be directly convert. You don't have to specifically write your shader for Unity. It will just work seamlessly. As you can see on this slide, I mentioned that we support ES also on the desktop. And I would like to just mention something about this, because I think it's pretty important. So, why would we want OpenGL on desktop? And to answer this question, I would like to point out a course this week, which was an open problem in real-time rendering. And one of the panel question was about production cost in games and what technology we need. And I think one of them is ES on desktop, because it allows the developer to significantly reduce his iteration cycle. So when you are a C++ programmer, to really understand the problem, it's when you compile, you don't want to recompile all your file, you just want to compile the file you just modify and run quickly. And for a developer, an artist on Unity, it would be the same. You plug your mobile on your mobile on your desktop, and then you need to build a player and upload it, and this is actually very long. While where when you have OpenGL ES on desktop, what you can do is things like modifying your scene, just click play, and instead of having a process of maybe 15 minutes, you reduce this process, this iteration time to 5 seconds or something. So that for a developer or an artist, it's a very different experience. Yes. We are also considering some ideas, but it's still not done, where you could just plug your mobile and Unity will detect what's on this device and you will run exactly as if it was running on this device. So I think we are going to continue working on this. So Unity 5.3 will be available in December, but we have alpha and beta program, and if you are interested in our OpenGL support, I will be happy to speak with you and include you to the alpha and beta program. And the alpha should open pretty quickly. So that was it.
Right, I have a quick announcement. If you were here 2 years ago in LA, in this convention center, and you had a popular OpenGL book, and you had a book signed by their authors, then you forgot it here 2 years ago. But we still have it, so please come talk to me.
So this time I remembered to plug in my laptop, because it'd be nice if it lasted through the session. Wake up. It's not looking good. There we go. It was working before, I swear. That's right, my textures are incomplete. That's right, it's in Hector Map Linear. We totally don't want to try to move this to another laptop. We want to make this work. Did we have a problem with snapping up? This is awesome. Okay, well we may have VGA technology. We did at some point.
Yeah, it's featuring it.
We're going to have to do that. Sucks. So this is going to be great when Tobias gets up because we have to change laptops again. I can't hear a word you're saying. Okay. So you've been having a good cigarette? Sorry, you want to try? Which demo do you have? You know, every other SIGGRAPH I've brought my bag. Hasn't always worked. Better than this. I'll talk faster later on to make up for it. Hey, another triumph. Now I have to find out. This might work. Okay, all that work, and my slides aren't nearly as pretty as Barthold's. We already did that one. How do I scroll through this? We already did that one. And that one. That's the one. Sorry about that, folks. So it's basically just me, except that we're going to have a couple of guys from the ES working group come up later to talk about their what they're doing with 3.2. So I'm going to cover what the state of ES today. I'll give a lightning overview of 3.2, and I'll talk about the changes to the conformance program, and a little bit about the future. So, here I am in my Vulkan t-shirt, and there's lots of Vulkan t-shirts in the room, and it's awesome, and I'm really excited about it. It does not do to forget, because every so often I get gobsmacked to realize that, actually, although that feature is very exciting and bright, that OpenGL ES is kind of an amazing success story. This is Gartner Group figures, 1.7 billion devices will ship in this calendar year, which puts the total number of ES platforms ever sold close to the number of people. So that's sort of mind-boggling. A lot of it is still ES2, which for those of us who love the new features is kind of disappointing, but it is a reality of the market. Still being used heavily in, mostly now in really entry-level devices in Asia, in India, but lots and lots of ES 2.0 devices going into phones and tablets, and the dominant device in smart TVs, automotive, etc. Also finding a new niche in, I said ultra-low power here because when I say IoT, it makes my teeth hurt, right? Wearables. All those marketing words. But there are these new form factors coming which require ultra low power 5 devices, and ES2 is working really well for those. New parts still coming out, new architectures coming out for ES2. And of course, today at least, ES2 is the foundation technology for WebGL, defines the core feature set. And although ESSC hasn't decided what they're going to do, it's probably where they're going to start looking. However, ES3 is coming along fast. Thank you, Unity, for maintaining the normal device survey. It's awesome. ES3 is up to 40% of the devices hitting the Unity survey. So that's pretty exciting. We're starting to see stuff go on. And it is the de facto standard for making a, if you're taking yourself seriously as a high-end phone or tablet manufacturer, you're shipping some version of ES3. Skipping over the prehistory, and so 3.0 came out in 2012 at SIGGRAPH, and after it came out, it had been a huge effort. It took us 5 years. After it came out, we realized, oh shit, we forgot compute shaders, and we really need them. So we turned around and did the fastest job we could of putting them in, released ES 3.1 with that, and it was ready at GDC, so we released it there. First time we've ever not released a spec at SIGGRAPH, at least an ES spec. But later that same year, when Google announced that they were going to expose it in Android L, they also introduced a large extension called the Android Extension Pack, which had a lot of features in it, and they were features that, because Android's an important program, it turned out there was tons of hardware in flight that was going to deliver this. And we view our #1 mandate before almost anything else is expose what the hardware can do. Never hide hardware from the programmer. So after some discussion, we decided that we needed to do an ES3 too that would expose that capability. So that's what we have done. So running through, this is going to be short because we are short on time. But briefly, the goals, first and foremost, as I said, expose the hardware. AEP was defining de facto a class of hardware that needed to be made visible. We allowed ourselves to add other stuff, but only if it was stuff that all of the AEP hardware in flight could do, because we didn't want to delay adoption any longer than necessary. We also had a goal that we didn't want, because Vulkan was working 24/7 and secret. It's no secret, guys, it's all the same people doing this work. We wanted to make sure that we got this done without delaying Vulkan. And I think we've succeeded in that. So what's AAP in a nutshell? It's a meta extension. It includes the 20 extensions that you see there, plus some increases to implementation-defined min-max values. So it's cool, but if you go to try to say, oh, I think I'd like to learn AEP, I imagine Google has awesome documentation for it. I hope so, because we don't. Right? If you go and read the extension, it's a text file, and it says, go read these 20 text files, each of which is a handwritten delta against the specification. Now do the git merge in your head, and I hope you don't get any conflicts, because if you do, you're out of luck. So that was another motivation for doing this, was to establish a clean base, resolve those conflicts, which there turned out to be some of, and get a clean spec out. So, running through this in a nutshell, and again, no pretty pictures like Barthold had. Clearly the glamorous, sexy feature is the pipeline extensions, tessellation and geometry. I was a little saddened at the unsolved problems in real-time rendering course yesterday to hear Natalia say, of course, using tessellation to do what I want to do with it is an unsolved problem. So that's kind of sad. But there are things you can do with it, and it's in the hardware, so it is in the specification. Something I'm extremely excited about, in ES 3.1, we had the compute functionality of image read-write and atomics and stuff, but you could only use it in a compute shader. At least it's only required in a compute shader. With 3.2 and AEP, it's required in core that you be able to do those in a fragment shader. A minimum of the same number of binding points that you have in compute shader. So that's really cool. Per sample processing, you can do it two ways. You can get the sample mask yourself and work stuff out, or you can just say turn on sample processing and have the hardware do per sample fragment shader invocation. There's extended blending operations. So drawbuffers index gives you a lot of flexibility as far as what blending modes you use where. Blend equation advanced gives you a whole bunch of new blend formulas that you can turn on. KHR debug. I love KHR debug. It's great to have it, and it's great to have it standard. So it's in core now. It'll be there. And a ton of texturing stuff, including ASTC LDR, which I'm delighted about. Cube map arrays are awesome. Actually, all this stuff is awesome, so that's great to have. Sorry, there's one AAP feature that we did not carry over. That is texture sRGB decode. So the deal is, that's reasonable functionality, it's good to have, but it's kind of niche, and after discussing it with the Android guys, we didn't think that exposing the functionality this way was right for a core specification. The right way to do it is with texture views. We didn't actually add texture views because we didn't have time to define it, but you might infer that maybe we will. Texture views is, we think, the core-friendly, future-friendly way to expose this functionality. Of course, if you're on a platform that's going to support AAP, it's going to have this extension, so you'll still have it, but we just didn't put it in the core. Then there's three things not in AAP that we also added. First of all, by long-standing request of the WebGL guys, KHR robustness. So this is critically important if you're going to move forward with running untrusted content. You can kind of validate ES2 content by scanning the shader carefully and by scanning the index buffer and stuff. There's no way you can do that in 3.1 when you've got, it becomes the halting problem in order to determine if you're ever going to write outside a buffer. So it's really important that we have the ability to opt into saying, check all my memory references and do not let me access any of the process's data. And don't crash me if I go outside. So that's cool. Draw elements, base vertex, and other requests. This is many IHVs requesting this. It basically, from my point of view, it's a way to have to do a lot less reminding of vertex attributes. So that's a good thing to have. And we all had support for it, so it's in. And finally, my favorite, color buffer flow. I am so not going to talk about why we didn't have it before, except to say that it's one of those tragic things that happens when 21st century technology meets 19th century patent law. But anyway, we have it now. I'm not going to say anything else about it, and if you ask me questions, I'm going to stick my fingers in my ears. So, 3.2 spec came out Monday. Thank you to John Leach, spec editor on behalf of Khronos, and Rob Simpson from Qualcomm. Thank you also to Ben Bowman of Imagination, who did a heroic job of doing the man pages and didn't even get to come to the meetings and drink beer because he's been at home a lot lately. The reference compiler Barthold talked about, not quite up to 3.2, but it's got most of AAP. John was telling me he thinks he'll be done by the end of the year. And from then, the port to 3.2 is easy because it's basically all the AAP features with different names. Conformance test also not ready yet, but in progress. We have an RFQ out. Part of our goal of not slowing down Vulkan was we decided to completely outsource the conformance test creation. We have a lot of the tests already because of the extensions. So that RFQ is probably going to close in a couple of weeks. Something radical we're doing that we've never done before, we're going to put the conformance test into open source. And I have a little more to say about that. That's, by the way, part of the RFQ is to do the background work that needs to be done for that. So first of all, why not? Well, partly laziness, partly institutional inertia, but we are trying with Vulkan and with many things to change the way we operate to be more open. Going open source seemed like a sensible thing to do. We also saw lots of advantages to us. We've been writing the tests, and we're all, spec nerds and IHVs, and we are really good at writing tests for weird corner cases that your program will never hit anyway. We're not so good at finding the cases that the ISVs have been finding where applications are doing things that are not according to the spec and it works, or they're doing things that are according to the spec and it doesn't work on some implementations. they've been finding those things, and they've been telling us, particularly Christoph's been telling us, you make it open, you make it easy, and I will put, when I hit a problem, I will put that in there. So, you know, it's not that you have to do that, but we would really love it if you did. So we decided to make it as easy as possible. Another reason is to share code. The Android guys have been doing awesome work with putting tests into AOSP. The DEQP test is publicly available, open source. We could have just pulled it in, but it seemed better and more friendly to say, let's just open the whole thing and manage it together as a group. We have some guys on the team who do work with Piglet. We haven't really talked about if there's anything we can do, but we certainly want to have that door open as well. So just a few issues that we have to solve. Right now, we're running it internally on an internal Khronos GitLab instance. For technical reasons, we're going to have to keep that, but we will make it available through GitHub exactly how we do merges across, which is master and which is a mirror is going to be not yet settled yet, but will be settled soon. But anyway, you will interact through it through GitHub. You'll do clones and merge requests against GitHub. The reason that it's not trivial to do this is that the test has a long history. It goes back to SGI. It goes back before OpenGL ES. It's got code contributed through years by various people, most of whose companies no longer exist, under license terms that don't let us open source them. So what our contractor is going to have to do is their first job is factor out the old crufty stuff and put that into a package of tests which will have to stay closed for the foreseeable future. But to get all the new stuff, which includes all the draw elements tests, all the and many of the new tests that we've created, will all go into the open package, which will be available through GitHub. So if you're an adopter or you have a license from Khronos to run the full conformance test, what you'll do is you'll clone the open part, you'll drop the closed part into it and just say make. It'll detect that the closed stuff is there, build itself, and run the whole test. If you don't have the closed test, it'll run everything that you do have. So that's the plan. It should happen before the end of the year. It's mostly a matter of getting the contractor on board and getting it worked out. I'm taking too long, sorry. I just wanted to say a word about, so here I am in my Vulkan t-shirt and working like mad on Vulkan and loving it. Does that mean OpenGL ES is kind of gone or its day is past and it's no longer interesting? This is my view. I haven't really checked this with the working group, at least not officially and collectively, but this is what I think happens. No question, lots of people have been trying to write stuff in OpenGL ES that just doesn't work very well because it has vicious frame rate or latency requirements, or it needs a level of control and determinism that OpenGL ES drivers just can't give you. So those apps will move to Vulkan. That's what it's for. That's why we're doing it. So that's a class of apps. There's going to be another very large class of apps, maybe more in terms of the numbers, for which OpenGL ES will still be the easiest way to get it working. If your main, if your view for the application you're writing is that, man, once it is functionally correct and rendering the right images, I'm almost done. I have to do my testing and I have to do cross-platform testing, sorry about that. But I don't have to spend half of my development time trying to get the hitches out and trying to get the frame rate up. For those apps, write them in ES, it'll be faster. You'll get it done quicker. Also, ES is still going to reach the largest number of eyeballs. If you stick with 3.0, you get Android, iOS, and all the desktop. And that is the easiest way to reach a large number of people with a single code path. In the meantime, so OpenGL ES future is not, we don't stop with 3.2 probably. I already mentioned texture views. There are other things that we could have added that weren't in enough hardware to make it sensible, or that we didn't think we could get done in time for SIGGRAPH. So I think ES has a significant future. I don't know when the end is. If we get something better that meets those needs, that'll be the time. Or if we come up with something ourselves. But this is where we are today, I think. Jumping right ahead because we have so little time, I should have said, we don't really have time for Q&A because we're going to keep you longer than you wanted to be here anyway. We're all going to be here after for the party. We may have time for some Q&A and we'll try to do that. But I don't want it to stop for that now. We have a couple of guys who have ES News who want to come forward here. Now I'm wondering if I'm going to have to reboot my laptop every time.
Hi, my name is Piers Daniel. I'm a driver engineer at NVIDIA. And what I just very briefly want to say is that we have made available OpenGL ES 3.2 drivers on our website. You can see the URL out there, or just Google it and you'll find it. These drivers are supported on Windows and Linux with our GeForce 400 series and above. So that's our foaming chips, our Kepler chips, and Maxwell. So this will give you a great way to start developing your ES 3.2 content now, so that when the mobile products come, you'll be ready to deploy on those. And talking of mobile products and mobile processors, this is an NVIDIA Shield, and this guy will support ES 3.2 in an upcoming over-the-air update. And this little guy is $200, and you can just, as soon as we ship, you'll be able to test your ES 3.2 content on this guy too. And our Shield tablet will support it later in the year as well. That's it. Thank you.
Tobias?
Yeah, so I'm Tobias from Imagination of the Talk later in Vulkan. I just realised embarrassing, we're all wearing Vulkan t-shirts. So obviously we all welcome it to TS32. So OpenGL ES 3.2 with support on all our Series 6 XT cores onwards. We've got AAD currently shipping drivers, and we will be having ES 3.2 available shortly. I just wanted to say that we're going to continue to support it as long as it's needed by the industry, and as long as it keeps moving forwards. Obviously, we're going to talk about Vulkan in a minute, so don't think that we're banned. There's a bunch of great new features, as Tom said. Photo rendering, yes, I love that one too. And the debugging stuff, blend modes, and dynamic indexing shaders, which is a slightly weird one, but very, very useful. And that's why it's coming.
Thank you, Tobias. Oh, I seem to have lost a slide. That one. Can I have this slide, please? And I'm going to reboot this thing again. There we go, because it's a cool slide. Okay, so now we move into the future-looking Vulkan mode. And the way this is going to work, we've got, maybe not that much. We've got too much material, but not that much too much. Okay, so the way it's going to work, I'm going to give you the very dry and boring chairman's managerial view of how the project is going, very, very briefly, and then turn it over to working group members to talk about specific things we've done. I'm kind of assuming that, how many of you were at the new APIs session? Quite a lot. Good. I'm really glad, because we're not going to cover any of that. At least partly. Also, if you've ever seen any of the stuff that we put up at GDC, which is all available for streaming, we gave quite a bit of a disclosure back then in March. So we're going to kind of focus on what's different and some corners of this that have taken up the working group's time recently. So we'll have Jens to talk about the SDK and ecosystem work. Alon will talk about how you connect Vulkan to Windows systems, a surprisingly difficult problem to solve. Jesse Barker will give you a lightning tour of the major changes. So if you saw the walkthrough that Graham Sellers did at GDC, he's going to tell you everything that's changed since then. And then Tobias will add some color to this by going through and cherry picking some of the high spots of particularly cool stuff about Vulkan. And then we have a long list of guys who are it's going to go jack-in-the-box time, because we're going to have guys standing up, giving a little bit of news and or showing a demo. And that should take us to beer time. So the dry boring part. Timeline. So this project started as a kind of a skunkworks project with a kickoff meeting at Valve back in 2014 in July. And we all said, yeah, we really want to do this. Let's go ahead. At that time, AMD donated Mantle. I was going to put in the logo, but I didn't have time. But thank you, AMD, for Mantle. We started from there, and then we mutated it. And if you know Mantle, you'll recognize some stuff, but it's changed a lot. In August, we went public with the plan at SIGGRAPH, so that was exactly a year ago in SIGGRAPH years. We then kept madly working. We had basically solutions to all the major technical problems by January, kind of hit a fixed point, took a deep breath, and looked at what we had, and then said, oh, that sucks. And no, it wasn't quite like that. But then we moved into a refinement phase. And we started consulting with some people outside the working group in a casual way. At GDC, we went public with what we had, both in the main conference and at the Khronos events. At the same time, we went into relatively high gear with talking to a population of developers that we knew who were willing to suffer with the incredibly crappy documentation and obtuse processes that we had to get some feedback. And we got some great feedback from them. We made a number of changes to the API in response. So thank you to them for putting up with that pain. We went at the end of June into a kind of freeze. It's not that we're not going to change the API anymore, but we wanted to give ourselves some space to get the spec written, to get an SDK built that would implement it, and to start doing conformance, and sort of get those up to where our thinking was, so that we could then step back and take another look and see where we're going. So that's kind of ongoing now. We're still making changes, but they're moving more and more into the margins. Where we think we are, we're on track to deliver a spec at the end of this year. That's what we said we would do at GDC, and it looks like we're on track. We're not going to be way early, but we should make it. The critical path is turning out to be creating the spec document. We kind of know what the API is. The SDK here is in pretty good shape in performance, but we're all pitching in to try to make this happen. My hats off to our heroic spec editors. They have a tough row. We're doing everything we can to support them, and we're getting contributions from guys like Jesse Barker, Dana Koch have been pitching in chapters, and that's awesome. Conformance is in particularly great shape, which is awesome. It's usually the last thing we think about, and this time we're really doing it right. Particularly thanks to Google, who have volunteered Peter Halos, one of the world's experts on testing graphics APIs, to be the project manager. Also some engineers to work on it, and we have engineers at many of the member companies. We've had code contributions from Imagination, Intel, Qualcomm, Samsung, and code reviews from others. That is fantastic. So we are kind of expecting the conformance test to be ready about the time that the spec is done. And that's all I'm going to say about project status, and let the guys talk about the technical situation. So Courtney, Jens, theoretically you've got 5 minutes. Good luck. Dum, 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 dum.
Okay, I guess I'm good to continue. My name is Jens from LunarG, and I just wanted to share with you guys a little bit about the work we've been doing. It's really been great that Valve has funded LunarG to support the Vulkan ecosystem from the beginning, and we've been privileged to be involved by creating the tools that will support this, and that's all meant to go out in open source. So this is stuff that's under NDA today. We're building a repo that will go out open source the day the spec goes out. And we're putting all this together in an SDK, and we're providing support to developers via a portal we call LunarG. And if you want to get updates on when that is available, I encourage you to go to lunarg.com/Vulkan, and you'll be able to sign up there. This is just a screenshot of the portal that we have running today. We have over 200 users right now within the Khronos community that are banging on the SDK, submitting issues, helping us improve the documentation, validation layers, the loader, and the tracing and the tools that we've been developing. And so I'm going to have Courtney come up here, who's our chief architect on this project, and he's going to go into a little more detail about what's involved with these open source components and how we're putting it together. Courtney?
Hi folks, I'm Courtney Gelslider, and we will get started. Let's see, press. Okay. All right. One of the big things that when Vulkan got started was we were looking at the OpenGL environment and saying, gosh, what are some things, now that we're doing a brand new graphics API, that would make it so much better than what OpenGL provided? And one of the areas where Valve stepped forward and said, you know what, you got to be able to trace these things, right? Why do we have to bend over backwards on every single platform doing weird contortions just to figure out what calls were being made by application X running on device Y? And that inspired the idea of this loader and the layer architecture. And as we explored that, we also realized, well, gosh, if you have this automatic binding thing with the API, you can implement what we're calling the validation layers and debug layers and innumerable other things that would extend that capability if you can insert into the Vulkan calls itself. So now we can check that not only conformance checks the drivers, but the validation is intended to help an application do the right thing for Vulkan. So make the right calls, make sure all the dependencies are met, and even, sometime in the future, provide performance feedback for an application to make sure that it's doing things in the most optimal way for Vulkan or maybe for a particular class of platforms, etc. I clicked, it didn't go. All right. Okay, so one of the critical features and why there's validation layers, right, is the driver does not, should not, will not do checking, right? Its job is not to do the validation checking as happens all the time in OpenGL drivers, right? If you're giving it the right stuff, there's no point. Instead, you put that into this validation layer architecture, and you can have it check everything and provide feedback directly back to the application about what it's doing wrong. And then because it's layered, when you take out the validation layers, those checks are completely gone. They have no impact on the application performance, right? And that's what Vulkan's all about. Get that performance, being able to do the checking, but when you're done with it or you don't need it anymore, it's gone completely. Some of the validation layers that exist today, I'm not going to try and read everything to you, but API dump, that prints out what the API is that you're doing. There's stuff around the draw calls, there's image operations, memory trackers, object trackers, so tracking the lifetime of objects, making sure that you're not reusing an object before it's actually available, stuff like that. Param checkers you would expect, just making sure your parameters are fitting within the appropriate range for the various functions. Shaders, PRV stuff, and then a threading checker, which is still being fleshed out to try and validate the API calls that care if they're being done simultaneously by different threads or don't care, and that is being done appropriately. That's going to be a really interesting area, right? OpenGL was painful with threading. This is going to be painful in a different way. And with that, we are done with layers. So it's on to Alon. All right.
Hello, everyone. So I'm going to talk about the most exciting bit of graphics, which is how one monitors it with operating systems. Before I do that, I'm just going to have a quick word with my other hat on from Samsung. So my name is Alon from Samsung Electronics, and I just want to extend Samsung's support for the Vulkan project. So Vulkan is very important for us in Samsung. We've been committed to the project from the beginning, and we're very keen to see it flourish and looking forward to it getting out there. We are planning to use, as Neil mentioned earlier, Samsung is planning to use Vulkan across both Android and our Tizen platforms. We're still evaluating its use, the use of Vulkan for vacuum cleaners. That's TBD, but you never know. There's some very cool robotic vacuum cleaners that we make. So without further ado, onto Windows System integration. So, the key goal we had with putting together Vulkan WSI was to have a good fit with the API. So the same model of giving apps more explicit control of what they're doing. And what we've managed to put together is one mechanism for presentation that works across multiple Windows systems, but without sacrificing too much. So we tried to find a sweet spot between modern operating systems and standardization. So I'm afraid no OS2 support plan quite yet. We've got Android, Windows with WDDM 1.0, Mir, Wayland, and X with DOI 3, all believed to work well with the extensions we've standardized. But I'm using the word extension because we've decided to make WSI an extension to the API. So, learning from experience, we want to make sure that whilst we unify as much as possible for as many platforms as possible, we recognize that some platforms may need a customized WSI stack if what we've put together doesn't suit them, and if you have no presentation at all, you may use Vulkan without any screen attached. Leave that possibility open. So we hope that we've achieved at least a very clean way for your frame loops in your application to run the same way across multiple operating systems, and we hope that the vast majority of platforms will use this. So, introduction to a few key concepts in WSI. So, platform is one of those words that can mean many things. For us, platform means Windows system or operating system. And for those of you that attended previous sessions or looked at some of the material out there, Vulkan has this thing called VK physical device, which represents one of the devices that you have in your system. And from that, you can find out what platforms does it support. So for most cases, you'd only have one platform like Android or Windows, but you may have cases in Linux where there's more than one platform available, and you can determine which device supports which platform for presentation. And then the physical device exposes which types of queues are available. In the presentations we've had previously, we've talked about capabilities for graphics and compute. One of those capabilities is for presentation. So you make sure that the queue you have is able to take present operations, which we'll get to in a moment. The presentation engine is just an abstracted name for either a compositor or a display, so the thing that will consume your presentable images. And the key thing in Vulkan WSI is this thing called a swap chain. So a swap chain is an array of presentable images, so VK images that are allocated by the presentation engine and are capable to be submitted for presentation. So this is a text-heavy slide. This is where the arguments went to and fro, and that's why it was, I think, a very healthy number of iterations. So we really wanted to make sure we got the allocation model right, and we had a lot of push to say we want to be able to have more control of which buffer we're rendering to, no last-minute surprises in what buffer you're getting. So the key thing is upfront allocation of presentable images. So from your device, you're able to create swap chains, and those are enumerated with multiple images. Now the application, the key point is there's joint control between the application and platform as to the order of presentation. So the application can create multiple presentable images. It can choose which order to present them, but it has to make sure they're acquired from the platform so that the compositor or the display is done using them before they're rendered. And we've developed a very clean mechanism for platforms to tell applications if it's necessary or it's a good idea to recreate a swap chain. So if you've resized the window, or if you've got a different orientation, so it may be worth recreating your swap chain. So finally, the key thing is about ownership. So for all you EGL swap offer fans out there, we've divorced the 2 bits. Yeah, I can see you there. We've divorced the 2 bits of swap offers. So presenting and acquiring are 2 separate operations. The time has come for that. And this diagram shows you the order of events. So the application submits these to a queue. Again, if you're familiar with some terminology in Vulkan, the images need and other resources need to go through transitions between different states. So you need to transition an image to be able to present it. Then you can present it to your presentation engine. So at the start, the image is owned by you, the application, until you've presented it to your presentation engine. From that point onwards, the image is owned by the compositor or display. And a little detail, there's a Vulkan semaphore that once you request to acquire an image, it tells you the presentation engine is done with that, so that's done asynchronously. And then you're able to use it in the application again. So that's WSI in short. There's going to be more details to come. And there's also one of the things that Graham Sellers mentioned yesterday, discussion about display enumeration control, which is something that some platforms are pushing for, which we are working on and would love to get more into. So that's it for me.
My name is Jesse Barker. I'm a software engineer at ARM, and for the last year and some, it's been really my pleasure to work with the rest of the Vulkan Working Group on developing the spec and the standard, and also to have worked on our own internal prototyping efforts that hopefully some of you saw at GDC to sort of guarantee that Vulkan would treat mobile GPU architectures as first-class citizens. So we're all very happy about that. So this is sort of a quick overview of the stuff we've done since GDC. It's all driven by the sort of overarching principle of Vulkan, which is predictability. And everything that you see here is sort of in direct support of that goal. Some of this stuff was left till after GDC, mostly to keep the horse in front of the cart. But basically, you see some stuff up there that's there to support the developer's experience with the API. Not necessarily huge changes, but very significant to the developer's experience with Vulkan. The remainder that you see are to enable implementations to optimize resource management and other internal sort of configuration-y things. And together, these all will allow the developer to focus more on their actual algorithms and less on trying to guess when the driver might actually do something kind of unexpected. So in the interest of sort of predictable API behavior, we've made a few passes over the sort of namespace, the types of objects, functions, and parameters. And this is sort of to ensure that the developer is clear why a given object is required, is a required input, or to ensure that each parameter, whether it's a structure field or a direct function parameter, is a clear input or output, but not both. And we originally had memory heaps in Vulkan, and we sort of pulled them out for a while, thinking that it was an overly complicated thing to have. But we've sort of discovered that the constraint space around sort of allowed versus required properties was a bit confusing without them, and didn't always express a viable choice when allocating memory to back-end object. And so we've sort of put them back in to hopefully simplify things a bit, at least we think so. Right, so to some of the sort of more enhanced changes, I suppose. We've updated the pipeline a bit. So pipelines have become sort of pseudo-template objects, and an application can create a derivable pipeline from which any number of derivative pipelines can then be created. An implementation can then reference compatible components during derivative creation. So you get increased efficiency in not only creating the pipelines, but also in switching between derivative pipelines, because the implementation has a bunch of extra information about the differences, which may be very, very small in switching between them. We've also added a feature called pipeline caches, which are sort of allow sharing between the components between these derivative pipelines. And the sharing has potential to mitigate the cost of sort of a relatively large number of these big, sort of static pipeline state objects. In terms of what can be shared, pretty much anything, any sort of components of the pipeline, your compiled shaders, the layout information around your resources, and sort of any other state that the implementation might find useful in deriving other pipelines. This is all quite implementation dependent. It could be theoretically, any or no pipeline state. That's kind of unlikely. The strong likelihood is that you'll share a lot of information about compiled shaders and other sort of metadata around that. But so because this is sort of implementation dependent, the total benefit of the sort of save and load functionality will vary a little bit by platform, but is expected to be useful across the board. And this is one of the features that we put in at sort of at the request of the outside reviewers that Tom mentioned previously in his talk. Command buffer management changes. So we now have command pools, and these serve a role in command buffer management hierarchy, sort of between the system allocator and the command buffers themselves, which need to both be created efficiently and also to be grown efficiently as you add commands. So this relationship is sort of analogous to the descriptor pool, which we already had, and the way that works in descriptor set management. And similarly, the sort of threading rule for command pools is that no two threads can issue commands that use the same pool at the same time. So that's sort of your threading granularity there. The pools can be created to be sort of single use or many use. In the case of many use, it has these sort of reset semantics that allow both the command buffer and the command pool to transfer ownership of resources of memory back up the hierarchy sort of on a discretionary basis. This provides a lot of flexibility for implementations to provide really efficient allocator behavior for command constructions. This also actually was one of the things that came in from our outside reviewers. So we put that in. We've changed the command buffers themselves, and now command buffers have a sort of concept of levels. We have two of them. They're called primary and secondary, and applications can use sort of whichever, can use more than one sort of style of building command buffers. You can have a flat arrangement where you just build primary command buffers and put all your commands in there, and that's great. It'll work just sort of the way that you'd expect. But for maximum flexibility and efficiency of building command buffers, applications might choose to take advantage of the secondary level buffers. This basically lets you call secondary buffers from the primary buffers. If you're using both levels, there's a little bit of a limitation in terms of which commands can go in the primaries and which can go in the secondaries, but it's pretty straightforward. The application this way can sort of thread the construction of a render pass a little better by breaking the pass into sort of multiple secondary command buffers and along with the primary, and dispatch them all separately. In addition to the sort of flexibility that this inherently provides, we also get another feature out of this, which we've sort of been calling multi-pass render passes, though I think this morning or yesterday in the course, I think Jesse used the term merged, which I think I might like better, at least personally. Your mileage may vary. At any rate, so we now have this concept of a subpass within a render pass. And a render pass is now described as a directed acyclic graph of subpasses, which really enables applications to provide even more explicit information about the layout of the render pass and any dependencies that exist between sections of it. So it really enables the implementation to do really efficient setup and execution of render passes. By building subpasses into secondary command buffers, the application can efficiently build complex render passes that also execute very efficiently. And the dependency chain that you provide gives the implementation enough information to guarantee that the subpass, say n+1, can read the data written to the previous render target during subpass n. And that, in a nutshell, is what multipass is. And I know you're all dying to ask, well, what can I do with that? And the answer is, I think Tobias is going to tell you. Tobias?
Sorry, guys.
Oh, yay. Okay. Hey, okay, we're good to go. Right, I will apologise if this happens again because I do actually have to switch to a demo, but we'll get there.
hopefully it's not again. Sorry, so I'm Tobias, I'm here from Imagination Technologies, and I'm going to talk to you about why we think Vulkan is great. So I'm going to cover the following topics. I'm not going to go into any detail right now about them, but there's sort of an overview right there. I'm also going to be presenting with a demo, which is implemented in both OpenGL and ES, OpenGL ES and Vulkan, sorry, and it's using only the core APIs, no extensions in these demos. The aim is mostly to highlight Vulkan's advantages over OpenGL ES, and we're doing that by applying many simple workloads. We're not using anything like ESC, multi-drawing direct, or anything like that. So I've noticed in the platform I'll be demoing on is Nexus Player by Google. It's running Android 5.1 AOSP build. It is a mobile class CPU and GPU, so don't expect massive performance out of it, and it will hit thermal limits, which means that now and then the clock rate will throttle. This is to be expected. So if I say the frame rate's not going down and then the frame rate goes down, it's really not me, it's just the lag. So the first thing I want to talk about is how Vulkan is one API for all platforms and all architectures. There is a single base API you can code against the core of it, and it's designed from the ground up for modern systems. So that means all tile-based architectures that you see on mobile and immediate mode frames like you see on desktop typically, they're all supported from day one. That doesn't necessarily mean that there aren't differences between these platforms. I mean, you've got OpenGL ES 3.1 as sort of a baseline on mobile, and OpenGL 4.5 as the top end on desktop. And so there's capability flags in the API to cover this, which is your typical sort of minimum maxims like OpenGL and sort of optional feature support as well. And when I say optional feature, this typically means something that could be supported by everyone. No one's architecture is locked out from doing them, but they're not available for whatever reason. There's also extensions, which will come in the normal flavors of vendor, multi-vendor, cross-ratified. And one of the new things when I'm press release is that we've now got feature sets as well. We're only really defining the mechanism for this, but the idea is that feature sets will define functionality levels, typically defining capability flags and optionally support to be guaranteed. And what Khronos may define some of these options is also there for platform vendors to define. Another great thing is it's an efficient API, and this is really important, especially for mobile, but always for any platform really. I mean, the idea is that the GPU should not have to wait for the CPU ever. We really want to get the cost of the CPU out of the critical path mostly, so you're rendering loop. We don't want you to be waiting on the CPU. And especially on system-on-chip platforms, so something where you've got an integrated GPU or you're on a mobile platform, the CPU and GPU will typically share thermal limits and power limits. And so if you're actually not using the CPU as much, you can usually push a bit more out of your GPU as well, so that's actually quite a nice thing. And if you're on a battery-based platform like a phone or something like with a really limited battery life like a smartwatch, you've actually got increased battery life, which is again very, very important. And there's quite a lot of ways we actually do this in Vulkan. One of the really nice ones, I think, is command buffer reuse. The idea behind this is that if you've got static content in your demo or application, you shouldn't have to need to recalculate anything. You really just want to resubmit the same work as much as possible. And in OpenGL ES, this wasn't really possible, but in Vulkan, because we have this command buffer, separation of command buffer generation and submission, you can actually make your commands into command buffer and actually reuse them again, even after they've been submitted. And they're not completely static. You can't change any state in them, but any resources they reference, such as images or buttons, you can actually update those. You might update a transformation matrix for your camera, or draw indirect buffers even, which gives you quite a lot of power. And the key to all of this is that the actual cost of submitting those command buffers to the queue, the hardware queue, is actually very low. Right, so now I'm going to attempt to switch to our demo. So wish me luck. Yes. Hey, we have an image. It's sideways, but we have an image. Yeah.
Let's go for the right direction rather than the resolution. Well, that's what else. Hey! Woo! Hooray, gnomes. Excellent. Yep, this is how it should go. Okay, good. So, this is the OpenGL ES demo. As you can see right now, it's maintaining a reasonable frame rate. It's a little bit unsteady, but that's mostly just on its camera work. So, the CPU is sort of doing a lot of work. What you can actually see is the platform is bouncing the main thread between two cores, which is why it's going up and down. It's sort of an average of how much work is being done. Now, if I can move the keyboard for British. Not that one. Excellent. Oh, no, it's still not that one. Okay, right. I can zoom out. Now, each one of these objects you can see, each of the gnomes, each of the mushrooms, is a single draw core. Like I said, we were doing lots of very simple workloads. You can see that the CPU load has shot up, the FPS has gone right down. The GPU is working, it's not really working that hard right now. It's just pegged by the CPU, and I can go out even further, and it's much, much worse. And this is because we're doing, I know how many it's involved. Oh, I think it's about 15,000 draw calls, 1,500 draw calls. So, no, sorry, 15,000. Okay, so if I switch to the Vulkan demo, there we go. Okay, so I've already zoomed out a little bit because the keyboard's switched up. However, you can see I'm zoomed out. The frame rate is still fairly high, but the CPU usage is, well, it's negligible. I can zoom out a bit further, and the same sort of story. They've actually been running for a while, so they're really quite warm, so I think they should be softened a bit. But as you can see, it's quite smooth, and it's running without really touching the CPU. If it's pegged on the GPU, not the CPU. Alright, here's the fun demo. I'll switch back to the laptop now.
We have a backup.
Right, Dominic is going to just point his phone at my screen rather than keep something around.
Rather than reboot again.
Yeah, okay. Sorry, it's still the phone. Amazing. So thank you to our wonderful cameraman. Thank you. Okay, so another really great thing about Vulkan is that it's really good at outputting HDMI. Is that it's really good at parallelizing workloads. So modern CPUs are multi-core, and the applications want to take advantage by using multiple threads. Now in OpenGL and GLES, it's not brilliant at threading. We've all sort of covered that. I'm not going into detail of why, but it's typically limited to a single rendering thread and maybe a resource streaming thread. Vulkan gives you a lot more options of what you can actually achieve. And there's a few things we actually have in the API to give you this. So one of the main ones is the idea of application managed threading. At least in the critical path, there's no guarantees made by the driver that calling something from multiple threads and modifying an object at the same time is going to be safe. If you try and modify an object from two threads at the same time, you'll hit a race condition. And one of the ways we've done this, achieve this, is by having no global state as well. There's nothing that's completely global and that requires the driver to lock in order to access it. I mean, certainly there's still system resources that will be behind the scenes, but as far as we can, we've given you the option of not touching that. And the thing I'm going to keep banging on about is the separation of command buffer generation and submission. Because we have this separation, you're able to generate command buffers on multiple threads while submitting at the end when you're done with all of them, which is very cheap, so you can do that on one thread.
Okay, demo time again, but hopefully no drama this time. Dominic, if you'd like to back down to the screen. Yeah. It takes on sometimes. There we go. Okay, good, lovely. Right, so in OpenGL ES, so probably just explain a bit about demo first. So all the nodes and everything else you're seeing is actually divided into tiles, and each of those tiles is a separate command buffer. As a command buffer comes onto the screen, it's regenerated, at least in Vulkan. In OpenGL ES, it's just some draw calls, you draw them or not. Because it's that situation in OpenGL ES, when I start speeding the camera up and streaming in more nodes, it's not going to do any better. It's just exactly the same as before. There was no static reuse of command buffers previously, and there's no threading now. So it's exactly the same as it was before. If I switch to the Vulkan demo, hopefully. There we go. Now, at the moment, it's going slow. There's not much streaming happening. It's going to be doing what it was doing before static reuse. If I speed the camera up, it's doing a heck of a lot more command buffer generation. So I believe per second to second, it's doing 400,000 draw calls total, 250,000 of which each second are statically reused, 150,000 of which are actually being generated on the CPU across those 4 threads. As you can see, there's actually headroom to do more than that, but we sort of tweaked it to here and ran out of time. So, I think we're going to have to buy a beer, aren't we? Don't make me laugh. So, one of the things we found quite important was the idea of a predictable frame, particularly for things like VR use cases. It's very important to have a predictable frame time and frame to frame. And one of the main ways we achieve this is with explicitness in the API. Queue submission, the idea of actually when you submit work to your GPU, really needs to be explicit. So in Vulkan, again, we have separation of generation and submission. When you write your command buffers, there's nothing happening on the GPU. It's just going to be baking those commands down into something the GPU can then later consume. And then only when you actually submit something to the queue is it going to lead to GPU execution of that work. If you looked at OpenGL ES or OpenGL, there's going to be some driving heuristics going on possibly. If you do draw, maybe it's submitting that draw immediately to the GPU, maybe it's not, maybe it's waiting for a flush or swap numbers, you don't actually know. In Vulkan, the application has an explicit choice over that operation, which means you can have predictable results frame to frame if you know exactly when it's happening. And also, I shouldn't wave my hand before I got it. My bad. Another thing that's very explicit is resource management. So the idea is that from start to finish, you tell the resource exactly when to be created, when to stop being created, and when it's ready, it's ready. There's no more of pre-warming assets or the idea of deferring data uploads until draw time or shader generation. All these resources are ready when the application decides. Resources are also sort of bring your own memory. You create an image or a read buffer, and then you ask how much and what type of memory you actually require for it. And then there's heaps and memory types that give you the information you need to actually make that decision on where you want to put the memory and how you want to allocate it. And obviously you also know exactly how much you're allocating, which is something that's not happening in GLES. The actual mapping of those memory objects to allocations is entirely under user control. So this leads to some interesting schemes you can do, which you can do in OpenGL ES, such as, let's say you've got 2 transient frame buffer attachments, and they're both accessed at different points. So say you've got 5 render passes. The first one uses something to do some temporary data into it, and the last one uses some temporary data, like depth buffer perhaps. You can actually use the same memory backing for both of those objects without really worrying too much about it, even though they could be different formats or different uses. And there's actually sparse features in the API which give you even more control over this. And finally, what I think is probably the most important, certainly from our point of view, is that it's designed for all architectures. It's what I like to say, what I'm calling architecture positive. The idea is that it's emphasizing all architecture strengths rather than trying to just put features in because we can kind of do it and then worrying about whether it's actually fast later. It has to work, and it has to work well as we put it in. A good example of this is the render classes. Now, GDC, we said they made render targets and loads and stores explicit, which was great news for tilers. We didn't have them. And as Jesse just alluded to, we have subclasses now, which allows you to chain multiple classes together and they can communicate via pixel level data. This actually means we have pixel level storage in the core API. And what that means for those of you not familiar with the extension is that for tiled architectures, we can actually keep data on chip between render passes without consuming any external bandwidth or in fact making allocations for these render targets to begin with, while still allowing immediate mode renderers to actually allocate the resources and use what they need to do. Last demo, hopefully. Well, for me anyway. Right, so at the moment, zoom back in just to let OpenGL ES cool down for a minute. And I'm going to add some render passes. So the first one, we've got a sort of color grading effect, and we're using RGBA 16F render targets, the HDR render targets. And then I'm going to have a second one, fun, and we've got a bit of a vignetting effect. It may not be coming out quite as well, but you can come see it. And the fact is, we're using about 63 megabytes per second of bandwidth, per frame of bandwidth to read and write these render targets. And that's a lot, particularly on mobile. And it's also allocating about 31 megabytes of memory to store these surfaces in. And that's because we're using the core API. Of course, I could use pixel level storage to get around this, but as I said before, we're using the core API. Now in Vulkan, the story is a little different. Because we have these render class objects, I can add my effects, and it should have no noticeable effect on the frame rate unless it says throttle. Yep, good, excellent. And the idea is we're only doing extra compute work that actually do the effect, but we're not actually consuming the additional bandwidth, and there's no allocation for these circuits, they're entirely transient. If you want to know more about that, feel free to come talk to me afterwards. And just to prove the point, there's everything turned on and going really fast with all of the render targets. And just to really prove it. Oh, what the? Thank you, didn't see that. Alright, there we go. There's the OpenGL ES one, and it is really, really struggling. It does not like that whatsoever. Get the over on the stage. Limber up. Okay, so in summary, Vulkan gives us Vulkan gives us a lot of control at much greater efficiency than previous APIs have given. And it's one API for all architectures, all platforms, and it gives a lot of advantages. I invite you to come see the demo afterwards. I'll be over there in the demo area answering questions if you have any. There's more information on the Khronos site. On our Imaginations blog, there is actually a description of the demo, where you can contact me on Twitter, and do not ask me questions now because we're running out of time. Thank you.
So while Jesse is setting up, we're moving into the last phase, you'll be glad to know, of the BOF. We have a number of short statements from members, including a number of demos, which means we're going to be in device swapping hell. And in order to minimize that, Jesse's going to do his slides from his own machine instead of mine, and just demo. But anyway, take it away.
This one actually worked. So I will be really quick since we're running late. So as most of you probably heard by now, multiple times, Android is going to be using Vulkan. We're going to be adding it to the platform. We think that it is a pretty good mobile API. We're pretty happy with it. And I'm going to mostly just skip this because it's redundant with what other people have said, and I want to get us done. So basically, it's awesome. We like it. We're going to be supporting it in a future Android release. So as an application, if you target a particular version of the platform, you know that the loader will be there, even if the device has an older GPU that can't support Vulkan. You at least have the basic support there to ask, what can this device do? You will be able to declare in your application that you require Vulkan if you do, and the Play Store will try to deliver you to devices that don't support it. And we're going to be including the shader compiler and validation layers and a bunch of other tools in the NDK, so that when you get the NDK, you have everything you need to start doing Vulkan work. As Tom mentioned, we are contributing pretty heavily to the test suite. We think this is vital to making a successful API, and we're pretty committed to seeing an exhaustive test. Well, exhaustive is a strong word. As strong a test suite as we can possibly make, and we will be enforcing it on all Android devices and updates to them. That's Vulkan. And finally, I want to kind of reiterate what Tom said. OpenGL ES is still the right answer for some applications for a variety of reasons. As he said, if you heard RS talk yesterday, he explained why moving may be difficult for some people. It might not be the right way to spend your time, in the short term at least. So we will be continuing to support OpenGL ES, of course. We're contributing to it. And if there's things that it makes sense for us to do as a platform to move that forward, that'll help developers, we'll do that. So I'm going to do a very quick set of demos. And the main point of these is we have the same code running on multiple Android devices from multiple vendors. So we're pretty happy about that. We've got a lot of support from Imagination, NVIDIA, and Qualcomm to work one of our OpenGL ES NDK samples in a very short amount of time. It doesn't do a lot with Vulkan. It does reuse command buffers, and it uses some of the dynamic uniform update stuff in a much more efficient way than it was able to do with OpenGL ES. Alright, so this is a whole bunch of teapots. Well, it will be a physically based shader with a bunch of varying parameters, and that one is running on an NVIDIA Shield. So switch. And it will be the same thing running on, oh goodness. Well, I promise you that one was the Nexus player. Like I mentioned, the Nation GPU, and we can show you later. I don't know. What? Okay. Well, let's get that one. A really truly magical presentation. This is running on Nexus 6 with a Qualcomm GPU. Alright, that's enough of that. Thank you.
This is a really good time to mention that we have all those tables against the wall. And the reason for the tables is that while you're getting a beer, when you get a beer, we will be having the guys who have the demos showing them, and I will be running back and forth and bringing them beer because they're going to need it. And now we're going to see if my machine will connect. If it doesn't, we have loaded the slides to a backup machine as well. So one way or another, this shouldn't take as long as it did last time. Hey! Okay, so we got lucky. Please welcome Dan Ginsberg from Valve.
right, I know I'm standing between you and your beer, so I'm going to talk really fast. Thank you for inviting us to speak at the Birds of a Feather. My name is Dan Ginsberg. I've been working for Valve on Vulkan since its inception. And since hosting the first Vulkan face-to-face meeting last year, we've been really pleased with the progress of the API, and we think it's the right way forward for powering the next generation of high-performance games. I wanted to tell you briefly about a little bit of work we're doing with Vulkan at Valve. Personally, I've been working on porting Valve's new engine called Source 2 to Vulkan. The engine has already shipped to customers with the release of Dota 2 Reborn. You can download it now off of Steam Beta. The Vulkan version isn't there yet, but we have seeded it to all of the desktop IHVs, and one thing that is very exciting is that they all have it running on their drivers. And to us, that's really a validation of a key design goal of Vulkan, which was by reducing the surface area of the API, drivers are much simpler and they've been coming up much faster, and we're just really happy with the progress of how all of the IHVs have drivers running. Intel is showing it running on their driver at their booth on the show floor if you're interested in seeing it. As Jens mentioned earlier, we're also very involved with LunarG in creating an SDK. We think it's super important to have a world-class SDK to make Vulkan accessible to developers, and to that end, LunarG has been doing great work on all of the tools that they talked about, which you've already heard about, so I will skip. The last thing I wanted to say is just give our view of why we think Vulkan is the future. Unless you're aggressive enough to be shipping a DX12 game this year, I would argue that there's really not much reason to ever create a DX12 backend for your game. And the reason for that is that Vulkan will cover you on Windows 10 on the same class of hardware and so much more from all of these other platforms and IHVs that we've heard from. Metal, it's a single platform, single vendor, and Vulkan, we're going to have support on not just Windows 10, but Windows 7, Windows 8. We're going to have it on Android, and all of the IHVs are making great progress on drivers. I think we're going to see super rapid adoption. And so, you know, if you're developing a game for next generation APIs, I think it's clear that Vulkan is the best choice, and we're very pleased with the progress and the state of the API today. We think it's going to power the next generation of games for years to come. So thanks for having us.
Okay, we're going to some new clever reordering technology where we minimize the number of swaps of devices. So we're going to skip the NVIDIA presentation. It appears we'll come back to it, but stick to things that don't require disconnecting this machine. So please welcome Zoltan Hortson from Kashanti Informatics.
Hi everyone, I'm Zoltan Hortson from Kishanti. I'm the Chief Rendering Engineer at Kishanti for 7 years. Kishanti is a team of experts engaged in graphics and computer benchmarking for more than a decade now. GFX Bench 5 is our latest GFX benchmark iteration aimed at recent low-level APIs. GFX Bench 5 is the first Vulkan benchmark and has an entirely new rendering engine. It is built on an in-house render API to cover the following high-level and low-level APIs: Vulkan, Metal, DX12, OpenGL Desktop, OpenGL ES, and DX11. This render API also has a basic shader translator, so we can use the same shaders on each platform. The focus of GFX Bench 5 is on low-level APIs. High-level API support is mainly for comparison and development. The GFX Bench 5 is working touch with Alien Beam, and the theme is a night scene with alien spaceship causing a tornado-like effect. We chose this to showcase lots of individual drop holes. The efficiency of compute and rendering interoperation allow us to demonstrate on-the-fly generated light source. So the current state of GFX Bench 5 is a work in progress and in beta state, and supports the version 90 of Vulkan. We are moving to version 138 very soon, and Android support will be available soon. The ATA is beginning of September, and the release candidate version is expected at the end of this year. So now let's show the video. So here is the video. You can see a lot of light bugs here, which are animated by compute shader, and they are also light sources. And you can see the tornado effect here with a lot of dropouts. Okay. Maybe yes. Great. Okay. Yeah. Great. So I would like to summarize the most important features of the rendering pipeline. It uses deferred rendering, but switches to forward rendering at the transparent objects. It is HDR rendering and using adaptive tone mapping. The lighting model is physically based lighting. Another feature is light shaft, which is based on a ray matching algorithm, and particle systems are compute based. I would like to talk about the rendering pipeline in details. We have 3 passes. In the first pass, we use a compute based. We animate the particle systems by compute shader. It is not just a single emission and advection shader. It also generates point light, which will be used in the shading pass, and we generate geometry for rendering. The second pass is a classic deferred rendering pass. We render to gbuffer using MRT, and we issue a lot of dropouts here. We also do the shading pass here, and using point light, spotlight, and directional light. The lights come not from only the scenery, but they are in the previously mentioned compute pass. The third pass is a forward rendering where particles, systems, light shafts, and beam effect are rendered. And in the last step, we have the most effect, which uses compute shaders to calculate average luminance, and after all the things, the final composition happens. So these are our future development plans. As I mentioned, we are moving to the new version of Vulkan, and we will add Android support. We would like to include more rendering features like dynamic shadows, image-based lighting, and enhanced fog algorithm. We would like to include more additional post-process effects like velocity-based motion blur, depth of field, SSA, or lens flares. And on the long term, we are looking into ways of exploiting the multi-tracking capabilities of Vulkan. Maybe, and we are thinking of stereo rendering. So, thank you for your attention.
Hello, I'm Maurice Dribble. I work at Qualcomm, and I've got a really short presentation considering we're running behind. Okay, so basically I wanted to tell you, well, more things that I'm going to tell you, but to keep things short, I will just sort of let everyone know that the Snapdragon 820 was announced this morning by Qualcomm, which is a really cool new SoC from Qualcomm, and I think the reason I wanted to bring it up today is because it has a lot of features that are really going to be optimized for Vulkan and really bring out the best in Vulkan. We heard about multipass and that GPU there, which is the Adreno 500 family. It's the first SoC we're releasing with the Adreno 500 level GPU. Will be better supported there. We are also going to have some changes to how descriptor sets work, which will make our GPUs have less drop overhead there. However, Vulkan does also work great on existing products. We'll be showing a demo after the presentations here on the Snapdragon 810, which has an Adreno 430 in it, and I think we're good to show the demo at this point. I don't know how to do that. Let me just get out of PowerPoint. Where's the cursor go? Hopefully it'll run in this. So, do I fit play or? I may have done this one. This used to work. We watched this earlier. It's going to be choppy here. 5 minutes per break. This totally sucks. I'm sorry about this because we did test it and it did work. And it's an awesome video. I want you to see it. You're at the back of the screen. There you go. We're so close. Slovak? No, we need okay, no, let's not. It's fine. Okay. Here's. Okay. Well, one last thing. So I think I'll show this demo sort of after the presentations, and you can come and see it. But the main thing we're showing off is that you can do a lot of draw calls in Vulkan. We've got versions running OpenGL ES, and this is about 10x faster in Vulkan. So it's really great API, and Qualcomm loves Vulkan. So go Vulkan! Hang in there, folks. We have 2 more speakers, I believe, Pierce and Slovak. So we're going to. You don't have to see this crappy machine anymore.
Should we try that? What? And we'll need open short. Great.
Alright, hi, my name is Daniel again. I'm working in the Vulkan driver team, working for NVIDIA. Just real briefly, a lot of this is people have said already, but NVIDIA, Vulkan is very, very important to NVIDIA. We think it's a great API. The most important thing for us is it's an open API. Anybody can contribute. There's no single platform owner that defines the API or controls the API. It's controlled by all of us, and we can contribute to it. And when we launch a new GPU, for example, we can launch extensions for that new GPU without getting permission from anybody. It's an open API. It can be used on any of our platforms, and it's very, very fast. We are currently developing a driver. Anybody who's a Khronos member or a Khronos Vulkan advisor can get our driver if they sign an NDA with us. And our goal is that when the specification is released later this year, that we'll make a driver public. That'll be for Windows and Linux, and shortly after for our Shield Android platforms as well. Now I'm going to show just a couple of the benefits of Vulkan. I'm going to do this on my laptop here. So this is a CAD application. And what's the cool thing about this is there's 11,000 draw calls happening to draw this scene. And in between each draw call, there are 2 state changes. And right now, this is running in OpenGL mode. One of the great things about the Vulkan driver on our platforms is that it's hosted by the OpenGL driver, which means you can do OpenGL and Vulkan from exactly the same app simultaneously. So the UI you see in the top left corner, that's all rendered by OpenGL. And right now, this GPU is, this graphics card is actually rendered by GL right now. And if you look at the top left corner of this window, you'll see that we're using about 5 milliseconds of CPU time to render this. Now if we switch over to Vulkan mode, you'll see that CPU time dropped down to just 1.4 milliseconds per frame. So that's like a 5x savings almost in CPU performance. Alright, so that's 11,000 draw calls per second. Now we're going to get crazy. And we're going to load a ginormous model. This model takes 2.8 gigabytes of memory. So it takes a little while to load. And it's 220,000 draw calls per frame. And then we're going to see where Vulkan can really shine in terms of CPU usage. So hopefully this loads. Like I said, it's a ginormous model. It doesn't normally take this long. Here we go. Here's the model. You can see that it's a little bit sluggish in GL. And we're using about, that's because I don't have my laptop. Okay, there we go, this one like it. Alright, so you can see this model is taking about 43 milliseconds per frame to draw all of this. And then we're going to drop down to Vulkan mode. This is single-threaded Vulkan mode, and it's reloading the entire model into Vulkan, so that takes a little while to switch over. And you can see we went from 38 milliseconds per frame down to 6 milliseconds per frame, which is a really good saving. Now, the other thing that really makes Vulkan stand out to OpenGL, this is something that OpenGL cannot do. Even if you write your app extremely well, you cannot do this with OpenGL, and that is scale well across multiple threads. So now I'm going to increase the number of threads to 2 and watch the CPU time go down even more. So now we're using 2 threads to submit all the work, and our CPU drops down from 6 milliseconds per frame down to 3.7 milliseconds per frame. And that's something that is unique to Vulkan. Alright, let's switch back to the slides. So we have exactly the same ginormous model also working on our Shield Android platform. This is using one of our software frameworks where you can write the same code and you can deploy it on multiple platforms, and we'll make this available as well. So the same code is going to be running on Android, so let's switch over to that. Right, so this is Shield playing Android TV right now, and we have a little Vulkan prototype app, which I will start right now. And this is the GPU model I was showing you earlier. Exactly the same stuff, same code, running perfectly smoothly on our little Tegra X1 chip. This is running at 60 frames per second, 11,000 draw calls per frame. Now I'm going to switch to something a little bit more challenging. This model is only half of the model I showed earlier, because 2.8 gigabytes is just way too much. So this one is 110,000 draw calls per frame, 2 state changes per draw call, and here we are running at about 23 frames per second. Same code, running on Windows and Android, mobile and desktop. That's all I have to say. Thank you so much.
Okay, you all are heroes. Our very last speaker, another member of the working group of long-standing Slavik Grajewski from Intel.
Okay, so my name is Slavik Grajewski. I work for Intel, and I'd like to show you the demo that presents the benefits that you can experience when going from OpenGL into a Vulkan. This is a simple application that demonstrates the benefits. It renders 2 million points using 200,000 joules per frame. This is not something that you would usually do, but this is to expose the driver overhead. On the left side, we can see the CPU power consumption and frames per second. They are repeated on the lower end of the left side. Then on the right side, we can see the load of the cores. In OpenGL, the application is running in the same thread as driver. So in this case, we are bound by the core 0. The other cores are more or less idle. When we switch over the application into Vulkan mode, what's interesting to observe is that frames per second increased significantly. The power consumption decreased noticeably, and because Vulkan API is multi-threaded, we generate the workloads in multiple cores, and we should see that even though the workload is spread across the cores, we can see that the CPU power consumption is low. This benchmark can be run also in lock mode, where we have the same amount of frames per second regardless of the API. And this is to show that in Vulkan we have some amount of CPU power consumption. And when switching to the OpenGL mode, we can see that frames per second remains the same, whereas the CPU power consumption increased significantly. On the right side, of course, we can observe the relevant load on the cores, which in OpenGL we are on core 0, in Vulkan we are spread across the cores. So that's all I have to say. Thank you very much.
So I just have 2 more things to say. One is, come back next year when we will write a completely different contract for our audiovisual support. And we will fix these props. To apologize for that. So there's a party going on. There is beer out there, and you are welcome to go get it. I am willing, anybody else, I think many of us are willing to answer questions if you want to do it collectively. Do we have a microphone for question asking? So we can do some of that, or you guys can corner us. You all know what we look like. Do people, you know what it looks like? It looks like we're not going to do questions over the mic. Come on down, grab us. I'm going to be here for the rest of the night. Jesse has to leave. Many of us, the rest of us, will be around until the beer runs out at least. So come talk to us. and keep your eyes and ears peeled. Thank you very much.